And the title of this report is to study the Hall coefficient of the given semiconductor and obtain the charge carrier density in each case. My name is Bhaskar Solagai. I am recently studying in Central Department of Physics, and the content of the report is like this. So let us move to the introductory part. When a magnetic field is applied perpendicular to current carrying conductor, a voltage is developed across it in the direction perpendicular to both current and magnetic field. So this phenomenon is called as Hall effect. And the voltage that is produced across the specimen is called as Hall voltage. So as we can see in the figure, these are the direction that are specifying the current, the magnetic field, and the voltage that is produced in the specimen. The current here is represented by I, and the magnetic field is represented by B, and the voltage that is the voltage difference, the potential difference that is produced in the specimen is represented by Y. So as we know from the experiment, the Hall voltage depends on three different factors. The first one is the magnetic field. The second one is the current density. And the third one is the width of the specimen. So what we can write here is the Hall voltage that is produced is directly proportional to the magnetic field that is induced there, and the current density, and the last one is the width of the specimen. So from this information, we can formulate the relationship between Hall voltage and other parameters. So as we can write, the Hall voltage is equals to RH, B, Jx, and small b. So Rs represents the Hall coefficient, and it is constant for the given conductor. The formula that we use to compute the result is like this. The Hall coefficient is equals to slope times T into B. T represents the thickness of the specimen, and B represents the magnetic field induced in that specimen. In second, the charge carrier density that is represented by small n, and it is calculated as 1 divided by Rh, that is Hall coefficient, and E, that is charge of the electron. So we have two objectives of this experiment. The first one is to measure the Hall voltage across the sample, and the next one is to measure the Hall coefficient and the charge carrier density of the sample. So the materials required are listed here. So as we know, we are doing this experiment in a virtual lab. So all the apparatus are already equipped there. We should only tune few things so that we can take the observational data. So there are two different setup for this experiment. The first setup is the experimental setup for finding the magnetic field in different current supply. So we will be checking how much magnetic field is induced by the two given magnets in different values of current. So this is our first work. And the second work is to find the Hall voltage in different magnetic field with a different current that is applied towards the specimen. So these are two different measure setups for this experiment. So now we will move towards the lab. As you can see here, uh, this is the setup for the virtual lab. And we have two given electromagnets. These electromagnets are connected to the emitter here. And here we have the Gauss meter, which is connected to the probe. So we put the probe in between the electromagnet, and we find the magnetic field that is generated. So the first step is to insert the probe. So to insert the probe, we need to click on the sword. So after this, now the first setup of this experiment is already fixed, and now we just vary the current and look at the magnetic field that is built between these two electromagnets. So the first initial is the 1 ampere current. So while we are supplying 1 ampere current to this electromagnet, then the magnetic field generated is 0.1482, as you can see here in the Gauss meter. So this is the value of the magnetic field. So now we keep on increasing the current, and we record the magnetic field that is produced by the electromagnet. So as we can see, if the current supply is 1.5 ampere, then the magnetic field induced is 0.2223. So we keep on doing this thing, and we uh, fill up these details in a table, and after that we plot a graph. So one side we put the value of the magnetic field, and in the other side we put the value of the current. So this is the first recording that we should do. So for the second setup, we switch from magnetic field versus current to the Hall effect setup. So this new setup is also not so much different from the previous setup. The first thing that we should do here is to insert the Hall probe. So to insert the Hall probe, we just click on the wood. So as you can see here, the current that is supplied to the electromagnet is 1 ampere. So this current here is the representation of the supplied current towards the electromagnet. And here are few other options. We can select the type of the semiconductor also. So for right now, I have selected the germanium, and we can vary the thickness also. So let us put the thickness at the nominal, and the Hall current means the current that is supplied towards the semiconductor. So what we do here is we find the values of the Hall voltage in a different current that is provided to the semiconductor in a different magnetic field. So first of all, we keep this 1 ampere constant, and then we keep on increasing the Hall current here. So let us switch to the show voltage uh, tab, and then let us do the first one. So when the Hall current is 1 milliampere, then the Hall voltage produced here is 28.756 millivolt. So this reading is taken on the millivolt. And let us again increase the Hall current. So if the Hall current is 1.5 milliampere, then the voltage that is developed across this specimen is 43.133. So we keep on increasing the Hall current, and the limit for this Hall current is 5 milliampere. So after we take readings of all these Hall current, now again we increase the magnetic field. So at the first table we have selected 1 ampere. Now we will be selecting 1.5 ampere, and we'll be repeating this same process. So in 1.5 ampere also, if 1.5 ampere current is applied to this electromagnet, and 1 milliampere current is applied, then the Hall voltage developed here is, as we can see, that is 43.133. And again, we will increase the Hall current up to 5 ampere, and then we will again reduce this to the 1 milliampere, and again we will increase the current that is flowing towards the electromagnetic field, and the same process is repeated until we get up to 5 ampere of current that is going to the uh, electromagnet. So this is the process from which we take the data, and then we record the data for our computation. So after we have collected all the data, so these are the observation. When the current is 1 ampere, that is 0.1482 Gauss is produced by that electromagnet. So all these data are plotted here, as you can see. So in the y-axis, we have magnetic flux, and the unit is in Gauss. So for the experiment, we convert the unit of Gauss into the Tesla. But for the graph, we have kept this in a same unit, that is Gauss, and in the x-axis we have current in ampere. So after plotting, we came to know that the a relationship between the current that is applied to the electromagnet and the magnetic flux is linearly increasing. So as we can see, the higher the current, the higher the magnetic flux. And in the next table, we have the recordings of all the Hall voltages in all the current supplied in all of the current supplied for electromagnet and current supplied for the mm, current supplied for the specimen also. So let us read some of the few data so that you can have an idea. So if we supply 1 ampere current to the electromagnet, and if we supply 1 milliampere current to the specimen, then the Hall voltage that is developed across the semiconductor will be 28.758 millivolt. So let us again take few examples. If 2 ampere current is supplied to the electromagnet, and if 2 milliampere current is supplied to the specimen, then the Hall voltage that is developed in that particular specimen is 115.023 millivolts. So this is the way how we deal with this data. So after we have collected all these data, now we will plot these data in an Excel to see the relationship just the way we saw it before. So this is for the case of 1 milliampere current. So now, as you can see, we will take these two columns, the column of current in ampere and the column of Hall voltage in which 1 milliampere current is applied. So this graph is the representation of these two columns. So now we need to fill up these 9 different graphs so that we can find the relationship between all those things. And here, as you can see, the equation is here, y is equals to 28.75x plus 0.001. So we need these values for the error analysis. So the slope of this curve is 28.75 and the constant here is 0.11. So eventually we will take care of these values while we are calculating the error in slope. So as we have already learned about the formula, so slope into T by B, and the slope for 1 milliampere current is 28.75. So 28.75 is written over here, and T is there, the thickness is there, and the magnetic field that is produced here is 1.48 into 10 to the power minus 5. So this value is taken from the first graph here. When 1 milliampere current is supplied, then the magnetic field generated is 1.48 into 10 to the power minus 5. So we have taken the same value to compute the Hall coefficient. So the Hall coefficient for the first case is 1.942 into 10 to the power minus 2 centimeter cube per coulomb. For the charge carrier density, we have the formula 1 divided by the Hall coefficient into E. The value of E is 1.6 into 10 to the power minus 19, which is the approximate value. And the value of RS is written over here, and the final result is 3.218 into 10 to the power 20 centimeter to the power minus 3. So we'll be doing all these things for all those currents. So we will have, in total, we will have 9 different graphs because we have 9 different conditions. So in all those 9 different graphs, we will be calculating Hall coefficient and charge carrier density. So after this computation, we will go for the error analysis. So as we know, the error in every experiment is inevitable. Hence, analysis of error after computing the obtained values is very essential. In this experiment, we will analyze the error that is found in the slope of the curve. So without error, in every experiment, we have some error. To analyze that error is one of the most significant thing while we are doing in lab, or we are preparing the report of lab. So in this case, we will find the del M, which is also called as the error in slope by this method. So while calculating error analysis also, we have 9 different graphs. and we will calculate the uncertainty in slope from this method. As we can see, del m is equals to 1 divided by n minus 2, and in the numerator we have sum of y square, and in the denominator we have modulus sum of x square minus sum of x whole square. So this is the formula that we already know. And we have I is equals to x. The I represents current, and that current is represented by x. So the current ranges from 1 to 5, and uh, this is the hall voltage. So let us again move to the our observational table. So here we are taking this column, the second column and the third column. So for error analysis, we have taken the second and the third column, and here the slope that is represented by m, and the current that is represented by I, and the I, and eventually the value of I is equals to or approximate to x, and the c is constant, which we have already calculated from the graph. So after computation, so the value of del m, or the uncertainty of slope, is 2.812 into 10 to the power minus 2. So we will compute for all these 9 different tables. And after that, we can say, we can narrate the result. Hence, the measurement of Hall coefficient, that is RFs, and charge carrier density, which is represented by small n, obtained from the Warsaw experiment, was found to be 1.942 into 10 to the power minus 2 centimeter cube per coulomb, and 3.224 into 10 to the power 30 centimeter to the power negative 3 for 1 milliampere current, and so on. So these all are the data that we have obtained from this given experiment. So the conclusion that we have here is the sample of the semiconductor was analyzed to observe Hall voltage and get the Hall coefficient. Since the Hall voltage is found to be positive, which implies the given semiconductor is of p-type. So as we have all the recordings of voltage in positive number, so we can definitely say the sample is of p-type. So that means the charge carrier, the majority charge carrier in the semiconductor is holes. Let us move to precaution. So while conducting this experiment, we need to care few things so that our experiment will be more correct and more precise. The first one is we must have a smooth internet connection. Without a smooth internet connection, it will be very difficult to record to do the experiment. And we should be mindful of the unit that is used in virtual lab. The next content is advantages of virtual lab work. So there are many advantages of virtual lab work, and these are the major advantages. So the first advantage is, from any part of the world, if anyone is interested to learn something, if any student is keen to gain some knowledge about this experiment, then we do not need to require any physical laboratories. We just need a compatible computer and a good internet connection, and we can do this virtual experiment and have a clear-cut concept on that experiment. The second advantage is it reduces the risks of hazards and accidents, which are very common in real laboratory. So in real laboratory, uh, uh, it have some hazards. Sometimes we need to deal with very high voltage of AC current, and sometimes we need to be very careful to select the capacitor while constructing a particular kind of electronic circuit, and sometimes the capacitor may explode, or anything may happen. So the virtual lab is free of any accident. We can do anything without exploding anything. It requires only internet and computer, as we already discussed. And the next one is, many students can be enrolled at the same time in a same experiment. So what happens is, in a real lab, in a physical lab, many students cannot be enrolled in a same uh, experiment at the same time. So This anomalies, this defect of physical experiment is completely thrown by the Warsaw experiment. The next section is for disadvantages. So even though it is advantageous, there are some disadvantages. The first disadvantage of the Warsaw lab is it do not provide the first-hand experience. The first-hand experience means while we go to the real lab, the physical lab, we touch those things, we build our setup with our hands, we feel those instruments, we calibrate those instruments, and we check all those instruments, either it is well functioning or not. So these are the things which generates the first-hand experience, and these things are very essential to learn uh, properly. So this is one of the major defect of virtual lab. So for example, if we are constructing some circuit in our electronic lab, we need to check all those diodes that are used in that circuit. We need to check all those capacitors. We need to check all those transistors. Uh, so it is working or not. So, but in virtual lab, we do not need to worry all those things. Those things are already there. They are already well functioning. So this one is the major disadvantages of the virtual lab. And the next one is not everyone is equipped with a very high performing computer and with a very smooth internet connection. So if you do not have these two things, then virtual lab is very irrelevant to you. And the last one is the probability of having error is drastically reduced in virtual lab. So this seems to be an advantage, but uh, error is very essential. Error analysis is very essential. While a physical experiment is carried on with a real person in a real time in a real life, then there are some errors which are uh, which remains there, which cannot be completely eradicated, and those errors are although useful to us also, so that we can say this experiment is done in a real setup by a by a real person, or not through a computer simulation. So the probability of having error uh, is sometimes good also. So for the acknowledgement for this virtual lab goes to the head of the Central Department of Physics for encouraging, facilitating, and providing this wonderful opportunity of virtual lab work. And this is the bibliography. And there are some of the essential Viva voice question. So this is all. Thank you for watching.